Hi viewers, in this video we are going to discuss about the three address code in compiler design. Myself Shankar, and let's go to the video. Three address code is an intermediate representation used by a compiler to simplify complex expression into a sequence of simple instructions. In three address code, there is at most one operator on the right hand side of an instruction. That is, no build-up expressions are permitted. Thus, a source language expression like x plus y star z might be translated into sequence of three address instruction as follows. T1 is equal to y star z as operator precedence. From this sub expression, we have converted sub expression based on the operator precedence. T1 is equal to y star z. This y star z is taken from this expression, and T1 is a temporary name for the three address code. And next, T2 equal to x plus T1. T1 consists of y star z. So here, as per the definition, on the right hand side, it has at most only one operand. So where T1 and T2 are compiler generated temporary names. Let's see one example. In the three address code is a linearized representation of a syntax tree or a DAG in which explicit names corresponds to the interior nodes of the graph. So the example is given. So here we have to translate the expression into DAG and three address code form. So let's see how we have translating it is. Right. So here for the given expression, we are constructing DAG. So that we have splitting this expression into two sub expressions, that is a plus a star b minus c plus b minus c star d, because here the common sub expressions with these two parts is b minus c. So that we have splitted the given expression into two halves. So for the two sub expression, the common sub expression is b minus c. So we have generated syntax tree with the DAG form b minus c, right? So minus is the root node, and we are deriving b and c as terminals. So b minus c we have applied, and b minus c is commonly applicable for this sub expression, this expression. So here the b minus c is applicable with multiplied with the d, and here it is multiplied with c. So this minus, that is b minus c, is multiplied with a, and it is multiplied with d. So in here, this part, the sub expression is over up to this, but here we have one more addition operation, that is it has to be plus with a. So a star b minus c addition with again a. So here we are using DAG representation, not general construct syntax tree, right? So DAG representation, which means that here we are referring the common names, the forms, and also the root node can, sorry, the child can have more than one parent, right? So this is the main advantage of the DAG representation, right? So as of this, the sub expression is over, that is a plus star a minus b c, right? So this sub expression is over. So this sub expression and this sub expression has to get addition. So here we have, this is one sub expression, right? And this is another sub expression, and these two gets added with the main sub expressions, right? So the DAG form is over. So the main advantage over the DAG form is it may have, the DAG may have more than one parent, and it can share the common sub expressions. For this given expression, they have generated three address code also, right? So here, so initially what we have said, so the common expression we have identified, that is b minus c. So the b minus c is assigned to the temporary variable name that is called t1. So already I told you that for three address instruction, right, it can have only one operator at the right hand side. Also the general form of this three address code is x of y, which means that it can have two operands and only one operator. So x minus, sorry, b minus c, that is x operator y. So at the right hand side, it has at most only one operator. So this operation temporarily stored to the variable called t1. So next, from the left hand side, so it has to multiply with a. So already b minus c is stored in t1. So t1 star a, it can stored in the temporary variable t2, and next it should get addition with a. So a star B minus C is stored in T2. So A plus T2, it is stored in T3. And next we have another sub-expression, that is B minus C star. The B minus C already stored in T1. So T1 star D. So it is stored in the new temporary variable called T4. And next we have to add this sub-expression and this sub-expression, right? So this will be stored in T3 and this will be stored in T4. So finally the temporary variable name T5 will store T3 plus T4, right? And next, the three address code is built from two concepts. One is address and another one is instructions. In object-oriented programming concepts, it corresponds to the classes. This addresses corresponds to the classes, and the various kinds of addresses and instructions corresponds to the appropriate subclasses. An address can be any one of the following. The first one is name. For the convenience, we allow the source program names to appear as three address in appear as address in the three address code. In an implementation, a source name is replaced by a pointer to its symbol table entry where all information about name is kept. The second form of the address is constant. In practice, a compiler must deal with many different types of constant and variables. And next one is compiler generated temporary. It is very useful, especially in optimizing compilers, to create a distinct name. Each name a temporary is needed. These temporaries can be combined if possible when registers are allocated to variables. And here they have listed some common type of three address instruction forms. The first one is assignment instructions. Assignment instruction may be in the form of x equal to y of z. So in this case, it has binary arithmetic or logical operations. So here x and y, x, y and z are addresses, and this operator. These are all operands. X, y, z. These are all operands, and op is operator. So here the expression is evaluated with y of z, and the result will be stored in the x. And next type of assignment is x equal to op y, which means that these are all helpful for unary operations. Essential unary operations includes the unary minus, logical negations, and conversion operators. For example, converting an integer to floating point numbers. And the next type of instruction is copy instruction. The copy instructions will be in the form of x equal to y. So here x is assigned the value of y. The next type of instruction is unconditional jump. Unconditional jump is there is no condition, directly it goes to refer the labels. For example, go to L, which means that when the compiler reads go to statements, directly it goes to L without any condition. That's why it is called unconditional jumps. The three address instructions with label L is the next to be executed. The next one is conditional jump. In this case, it has some condition. Based on the condition, the control will go to some labels. So here, if x, then go to L, or if false, x go to L. So in these instructions, execute the instructions with label L. Next, if x is true, or if x is false, respectively. Otherwise, the following three address instructions in sequence is executed next as usual. The next one is another type of conditional jumps, which means that if x relational operator y, if this condition gives true, then it goes to L. So which applies a relational operators called less than or equal to, greater than or equal to, less than or equal to, and so on. So it execute the instructions with label L, and next, if x stands in relational operator to y, if not three address instructions following if x relational operator y, then it goes to L, is executed in the next. So however, the conditional jump in the sense, it has some conditional, based on the condition, if it is true, it goes to somewhere, right? Yeah, that is labeled place. And the next one is procedure calls and returns. These are implemented using the following instructions called param x. Param x is for parameters, and call p comma n, this is for procedure, and y equal to call p comma n, this is for function, right? So in this case, if we want to assign any parameters for procedures or function, we can use param x. Suppose if you want to call procedures without returning any values, you can use call p comma n. Suppose if the function has written some value that assigned to some variable, then we can use y equal to call p comma n, right? And its typical usage of the sequence of three address code instruction is parameter number 1, parameter 2, parameter n. You can call the procedure with number of parameters. So here p is procedure name and n is number of parameter. So it generates the part of call of the procedure p of x1, x2 up to xn. These are all parameters. So the integer n indicating the number of actual parameters in the call p comma n, and is not redundant because call can be nested. That is, some of the first parameter statements should be uh, parameters of a call that comes after p returns its value. So that value becomes another parameter of the later call. The next one is indexed copy instruction. In this case, there are two types of the forms are there. One is x equal to y of I, and another one is x of I equal to I. In this such a case, the first case, the y of value in the array indexed ith value is going to assign with the particular variable called x. The another type is we have value that we are going to assign to the array's particular position. So there are two types of indexed copy assignment is there. So one is from the array position we are copying to one variable, or sometimes if we have value from variable that we can assign to the specified position to the array. And the next one is address and pointer assignment. So it will be in the form of x equal to ampersand y, or x equal to asterisk y, or asterisk x equal to y. In this case, the instruction x equal to ampersand y, which means that it sets the r value in the sense read value of x is to be the location value of a location value in the sense memory address. So whenever the memory address we have referenced over here, the address value is going to assign from the address, the value is assigned to x. And the next one is here y is the name, perhaps temporary, that denotes an expression with an L value, that is location value, such as a of I comma j, and x is a pointer name or temporary. So in the instruction x equal to y asterisk, so here y is a pointer or temporary whose read value means its value of y is a location. So the r value of x, that is read value of x, is made equal to the content of its location. Finally, this asterisk x is equal to y. It sets the read value of the object pointed to x to the read value of y. That is, the value of y is assigned to the x. And next, another one example is given for do while with generating three address code. That is, consider the statement do I equal to I plus 1 while a of I is less than of v. So until this loop is executed, the condition gets fails, right? So for this, we have to generate the three address code. There are two forms of three address code is generated. One is symbolic labels and another one is position numbers. So here L is labeled. So initially it's do while. So first it has to get incremented I value. So temporary variable t1 is equal to I plus 1. The incremented value will be assigned to the temporary variable t1. That incremented value now we are assigning to I. So here t2 equal to I star y, because here we are assigning a value to the array. So you just consider the size of one element is 8, right? So it may be a float, right? So the size of float or double. So the size of value we have to calculate. For that, we are calculating the base address called I star 8, that is assigned to t2. So now we are assigning a of t2, which means that this will reference the size of the element. That's why we are calculating I star 8, which helps you to allocate the memory location, right? So a of t2, that is assigned to t3. So now it is a of I. It's equivalent for a of I. So now it is checks that if t3 is less than v, then go to L. If the condition is true, then it comes to L, and again it increments I temporarily. that is assigned to I. From that, when next element, we have to allocate the memory. For that, we are calculating star 8 and assign to T2. Then A of T2 assigned to T3. Again, we are checking T3 is less than B. So again, this process is continuous until it gets fails. So instead symbolic labels is L, right? Instead symbolic labels, we can write the same code with the position numbers also. In this position numbers, we are writing the sequence number of memory numbers, right? That is 100 or not one something. So initially same code we are writing. T1 is equal to I plus 1. So which helps you to increment the I value. If incremented, which we are assigned to I. Next, we are calculating the memory size for the assigning location to the array. So it is calculated and assigned to T2. So A of T2. If T3, because T3 is A of I, right? So A of I is less than B. Then where we should start, if the control is true, that is the condition is true, then again we have to start from here, which means that we have to increment again, we have to calculate the memory address size, and we are assigning values. Then again we are checking the condition. So it should start from where? Here. So its position number is 100. That's why we have specified the number 100 over here. Right, so there are two ways of assigning labels for the three address code statements. One is symbolic labels and another one is position numbers. Thank you. Thank you all.